Okay, we'll get started. I'm James Preston, and throughout the course of this presentation, we're going to be talking about the wonderful world of the ESP8266 microcontroller. To get us started, can I have a quick show of hands? Who has got maybe 2 or 3 or more hours of experience on the Arduino platform? Just show of hands. Cool. Okay, leave your hand in the air if after that you've got experience on the ESP8266 or the ESP32. Good. Okay, so you guys can correct me when I say things that are wrong. We'll go from there. So the promise of this presentation is that I was going to talk about the ESP8266. It's a tiny development board, comes in a variety of different form factors and sizes. We'll look at a couple of them. This is the smallest one that I've seen to date. And this will connect to a 2.4 gigahertz wireless network. It can reach out to a RESTful API. It can send some data. It can receive some data. And if we do really funky things, we can make sensors out of them. We're going to look at 3 kind of imaginative use cases. Well, maybe not that I've come up with. One being you push a button, a light turns on, and something happens. The other one being you stick a piece of sensor in some dirt and it tells you how wet the dirt is, and the final one being an e-ink screen that we're going to plug into it that I was working on just last night. So the ESP8266 is a tiny little microprocessor, microcontroller, MCU, whatever you want to call it. The processor inside it is absolutely tiny. You know, we're talking 80 megahertz. It's a RISC-based processor. So if you think full fat PC at the very top, you then think Raspberry Pi underneath it. You then think microcontrollers somewhere towards the Earth's core as far as capability-wise goes. Tiny amounts of RAM for them to execute your code in. So this is a genuine case where you have to think, whilst you're creating your program that you're going to run on these, am I using RAM effectively? Am I using it in the most efficient manner? I mentioned that it can talk to 2.4 gigahertz wireless networks, so your BGN class wireless networks there. So 5 gigahertz is out. Equally so, it'll only talk WPA2 pre-shared keys. Yes, you can get WPA to work on it and WEP on it, but we're not talking 8021X or any super advanced authentication profiles. As far as flash memory to actually store our program on, that varies on the type of chip that you get. So the one at the very top left here being the kind of the smallest ones that you'll buy on Amazon in normally packs of 4 or 5 and equates to kind of between 2 or 3 pounds per controller. Those are normally between 512K and 1 megabyte of flash. The more expensive ones, like the one at the bottom left-hand corner there, which is made by a company called Adafruit in America, they normally have about 4 megabytes of flash on. As part of those different form factors, you'll get kind of specialty ones as well. So at the bottom right-hand corner, this has got a battery holder built into it. So a 3.7 volt battery, and it can use that to power the board independent of external power. Most of these boards will have built into them some method of USB serial communication. So you plug it into your computer, be it a Windows PC, a Linux PC, or a Mac, and you put the software on it. Sometimes you will need a programmer board, kind of like this tiny little thing here, and that works with the chips at the top left-hand corner there. So sometimes you get USB serial, and sometimes you just have to make it your own other way. Just like your normal Arduino platform, you'll have I2C and SPI interfaces. Think of these as like the USB of the microcontroller world. On the ESP8266, you only get one analog port, so the rest of those GPI pins are all digital based. So a closer look at one of the boards themselves. So this is one of the Adafruit Feather boards. So they've got their ecosystem of boards which are interoperable, that you can stack together, that you can plug into each other. You can see the main body of the kind of the chip, the microcontroller here, and then on the far right hand side we've got the antenna for it. That actual board is this size in real life, so absolutely tiny. And then outside on the periphery of the board there, you can see all those GPIO pins, the connector for the battery at the top left-hand corner, that's the big black block there, and then also the connector to micro USB on the far left-hand side. And there's been a good amount of traction as well about going from micro USB all the way down to USB-C now, so we've got a nice common connector between all of those boards. One of the important points to note is that boards operate on a 3.3 volt logic. So most Arduinos, like the Uno here, that will operate on 5 volt logic. When you're buying components, you just have to bear in mind you don't want to go and try and feed 5 volts into one of these just in case you accidentally blow it up. So out of the box, you will get whatever the vendor decided to put on it. In this case, one of the boards which I bought off Amazon, if I just plug it in, point putty or a serial session at it, it's just going to list the wireless networks. Not particularly handy. So we need some form of programming these boards. There are plenty of different options. So up here I've got Arduino, which is kind of C and C++ based, and then NodeMCU Lua, which is an interpreted language there. There are other options. So there's MicroPython and CircuitPython coming out as well for these boards. So if you want to choose some other IDE, some other method of programming these, absolutely crack on. The two that I've chosen are the two that I've got the most experience with. Now, when I say most experience with, about a year ago, over Christmas, I was getting bored and I thought I need a new hobby, I need something new to do. So I picked up my first Arduino R3 and saw what I could do. And I made some terrible soil moisture sensors that corroded over a couple of days. But, you know, it was an interesting thing to do over the holiday. After that, I thought, oh, wouldn't it be brilliant if I could take my soil moisture sensor and plug it into the internet, because everything should be plugged into the internet. And I come across the ESP8266. My programming background is absolutely minimal. You know, I taught systems, you know, PowerShell, that's me. So I kind of strayed towards the NodeMCU Lua side and did only the minimal stuff in C with Arduino there. But there are examples throughout this presentation in both. The one point that I've kind of got with the Arduino is there is a absolutely massive range of libraries to do all kinds of things. So if you want to have an absolutely massive LED grid and you want to program that so it displays an animated image, then absolutely crack on. There is almost certainly a library for it already. What NodeMCU Lua has as an advantage is there's a very small number but of very well documented libraries. So you can go to a single web page and it's got every library that's being compiled for NodeMCU Lua. It's not that many, but the ones which are in there work, and they work exceptionally well. So we're going to start out with a basic example for running Arduino or compiling an Arduino application to go onto one of these boards. The IDE for Arduino is free. You head to their website, you download it, you install it on your machine, and you get your first sketch. So this is your first program. And in theory, you could program that, which is completely blank, onto your board, and it would do absolutely nothing. But obviously, we need to do a little bit more than that. So we need to tell the Arduino IDE where to get the configuration for that board. We need to tell it about the ESP8266. So we head into File, Preferences, Additional Board Manager. We plug in a URL, which is at the bottom of the page there. We hit Update. We go to Boards Manager, and we then say, hey, can you download the ESP8266 board? And this will give us a massive library of all the different iterations of the ESP8266 board that are out there. So one's from the NodeMCU team, one's from Adafruit, one's from, you know, all of the companies that have actually produced these kinds of boards and have then submitted them to this GitHub repository. Once we've done that, and once we've downloaded the code for the board itself, we're then going to go plug into the serial port that the board is talking on, and then tell it about which board that we're talking to. So in the case of this demonstration, I was working on this Adafruit Feather Huzzah there. So with the downloading of that board information, you also get some examples for your board. So this is a good place to start to reverse engineer some code for your boards. So in this case, file examples, ESP8266, the blink example. And all this is going to do when sent to the board, and first it's going to flash it to the board, so you can see the time that it's taking with that blue LED flashing there, sending all the compiled information out to the board. Eventually we're going to start to see this red LED blink away. And that's the basic demonstration. That's the blink demonstration. Isn't that amazing? Hey! Right, so that's Arduino for us. So the Arduino IDE is a good place to start. However, it's got limitations. So, in Notepad++, you double click on a string and it highlights all the other places that string was found in your your script. That doesn't happen in the Arduino IDE without some massaging. However, if you are already using a tool like Visual Studio Code, there's a plugin for the Arduino IDE for Visual Studio Code, so if you're familiar with that. Another option, and a really good one to explore actually, is the Platform IO IDE, and this takes that original Arduino plugin and soups it up so that you can talk to not only the Arduino-based boards, but a load of other different options as well, like the Intel boards and all those of kind of other complicated things for IoT. So that's the demonstrations for Arduino. Now we're going to go on to NodeMCU Lua. The initial setup of these boards is a lot more complicated than in the Arduino IDE, but I feel that the benefit that you get out of that is absolutely massive, because you've suddenly gone from compiling your code, which on the ESP8266 and Arduino IDE on my PC at home takes about a minute, to flashing it, which takes another 30 seconds, to waiting for your program to execute. You know, there's a minute and 30 seconds there that I'm wasting. I like to iterate on problems. I like to work on them as fast as I possibly can, and Arduino IDE just doesn't work like that for me. NodeMCU Lua, on the other hand, is we flash an image onto the board, and then we can talk interactively with that board. So through a serial session, you're there sending commands to the board, and the moment you hit enter, it does that command. It's really quite nice for that prototyping phase, I find. So if you go and do a Google search for NodeMCU, you'll come across their website, available in both English and Chinese. So the people that made the ESP8266 board in the original, they're all Chinese, so all their documentation is natively in Chinese. People started to translate it into English. They then made it what I would call native English after some time. You look at their website and there really isn't very much on there, but you then go up to the Fork Me on GitHub and you then see their GitHub repository, and there's loads of information on there. And then we actually get to their documentation. So this is their documentation hosted on Read the Docs website. It is absolutely fantastically structured. There are some basic but working code examples on there, which I really like about this. As far as reaching out to find more information about these boards, the forums are a good place to start there. So the ESP8266.com forum, good place to start looking. Equally so on Reddit and some other platforms as well. So once you've got your first board and you want to start doing some things with it with NodeMCU, you need to choose what kind of path am I going to go down to get the initial firmware image onto there, and what am I going to do to not only interactively talk to the board, but also program it so that when you remove the power from it, it doesn't forget everything. The simplest route that I've taken, having a Windows PC, is the one that's highlighted in blue. So they've got a cloud-based tool where you can go and build the firmware image with the libraries included that you wanted, or with the packages included that you want. There's a flasher tool, and then there's a really dodgy Russian-hosted Java-based tool, which works. It works really quite well, called ESP-Blora. You download that, you spin it up, you hope it's not doing anything malicious to your machine, and you crack on. In reality, lots of people use this tool, so if there's something malicious in there, someone's probably spotted it already. So as far as the build website goes, this is a free service. You can donate the guy a beer or a coffee at the bottom of the page if you use it on a regular basis. It'll ask you which branch do you want to build the software from, which packages do you want to use, and really, quite importantly, do you want to use TLS and SSL on your board? Please turn that on. Even if you're not going to do certificate checking, just at least send it over a secure channel, just so people can't intercept the data. So one of the common misconceptions about these boards is they're not secure, that they don't have modern encryption. Well, the boards for transit do support TLS 1.2. Sorry, no TLS 1.3 support yet, but maybe it'll come eventually. They do support a very limited method of certificate checking as well. So you have to give it the root CA and it goes and checks against that. It consumes a lot of flash memory, of course, but you can still do it. So out of this kind of array of modules, normally I would choose the HTTP one. This allows you to do native get and put requests on the board. There's the encoder one, which is handy to convert data to base 64 and hex on the fly. There's the MQTT one, which if you've not come across before, we'll cover in this presentation as well. And also the SMTP one as well, for obvious reasons, to get some method of time checking on the board. If you're going to do anything with the analog to digital converter on the board as well, make sure you tick the ADC button. So once you've done that, and once you've pressed the go button, a couple of minutes later, you'll get an email saying, hey, the board or the firmware is now starting to build. So every time you go to that website, you're always getting the latest version of the firmware or the branch that you've selected. So that way you can make sure you're up to date without any massive effort. And then once that's done, you'll be sent another email with 2 links. One of them will support float and one of them will support integer when you're doing mathematical operations. One of the important points to note there is that the integer one will run faster when you're doing those maths operations and the float one won't. That's really the only difference, other than there's a small difference in file size. So if you want your code to execute as fast as possible and you're happy to work with just integers, tick that interruption and flash that to the board instead. As far as getting the tool to actually flash this firmware image onto it, you head to GitHub. PyFlasher tool is on there. It's available for both Windows and OS X, 64-bit, 32-bit variety. You choose the one that you want. You point it at the board, you point it at the firmware, you press flash, you sit down for about a minute as it churns through and applies that software image to the board. And then once you've done that, it is crucially important that you remove the power from the board and plug it back in again, or at least hit the reset button on it. This is kind of an important step when working with this NodeMCU Lua. Is on occasion you'll find, hey, something's just not working. I can't talk to my board. Something's gone horribly wrong. Just try power cycling it. Turn it off and on again. So once we've got that, now we get to the good stuff. Our board is now flashed. We can start to talk to it. We load up PuTTY. We find out whichever COM port it's plugged into. At this point, we're on COM 7. We set our speed correctly, and it's important that we turn flow control off. Now, what I'm going to do with this next video demonstration is copy and paste in pin equals 2 GPI.mode pin GPIO output to say, hey, I'm going to send some data to it, not receive some data to it, and I'm going to set that pin to high. Guess what that's going to do? Turn on an LED. Now, as I'm holding my phone, videoing this MCU, slowly doing what it's doing, I'm then very carefully copying and pasting the next line in. So my apologies when it turns on, and you can see me shaking and waiting to see what's happening, and eventually it will turn off. There we go. And that's my demonstration of NodeMCU Lua. Yay. So the 2 most basic getting started guides there. As far as this Java tool goes for actually flashing firmware images onto it, so you can talk interactively with it via PuTTY or your favorite serial communications application. But this tool, along with some other tools, allows you to actually take your code, upload it to the board, and make it permanent. That way, you know, the next time you remove power and apply power to your board, it's remembered. It's flashed it to the flash, would you believe it, that's on the board. So, buttons. I needed to get a Star Trek reference in here somehow, and I finally figured out how to do it. So here we are in the 24th century in a Delta Flyer with Tom Paris, and they've still got buttons. So, my first demonstration of today, well, not a demonstration, but an explanation is holding up a board. So the plan is I'm going to push a button, and I've got 3 of those on this board here. It's going to turn on the LED. That's then going to trigger the board to connect to Wi-Fi. Execute an HTTP post. That's going to talk to the Microsoft Cloudy service called Flow, and that in turn is going to talk to Todoist or Outlook or any of the other services that Flow can talk to. And then once it's done that, it's going to turn off the LED. So for a larger demonstration, and please excuse my absolutely terrible attempts at soldering, this is the board that I've got. So at the bottom there, the actual controller, and on the top here, we've got this board, which on the underside has some pins plugged in, has a little resistor there for the LED, and some wires to link all the ground of the buttons to the same place. So Microsoft Flow, who's used if this then that? Yeah, okay. Microsoft Flow is kind of like Microsoft's attempt at if this then that. If you're a heavy user of the Microsoft ecosystem, it's worth a look. Inside there, they've got loads of connectors, all of which are very well written for loads of Azure-y stuff. But there's also things like RSS, connection to Todoist, which I used as my kind of shopping list and my list of chores to do in the house, social media sites, SQL Server it can talk to, GitHub, Bing Search, Bing Weather, if anyone actually uses those services. So there's a massive long list of options there which you can talk through. So on the Microsoft Flow side, I've got a couple of different flows set up, and it's just like building blocks. So what we're going to say is when this flow receives a HTTP post on a long, complicated URL, it's going to reach into Todoist, it's going to reach into my shopping list, and it's going to add a reminder to get milk, because that's what these buttons are best at doing. And equally so, I'm one of those terrible people who forgets to empty the dishwasher, so why don't I set another one that when I just set the dishwasher going, I go and find my button, I push the button, and it puts a reminder in my house list to empty the dishwasher. Equally so, you can build in things like delays. So if you're a subscriber to the notion of allocating your time in 5-minute, 15-minute blocks, and perhaps you want some kind of notification once you've pushed a button that your 15 minutes is up, and don't feel like using your phone to do that, or any other means that someone might like, we send that post, we delay for 15 minutes, and we then send an email through the Outlook email service to say, hey, your 15-minute is up, with compliments from Microsoft Flow. So how does that look in NodeMCU Lua? You'll find throughout the course of this presentation that there are a number of white blocks. Most of the time, that's just me hiding an API key or the pre-shared key for my wireless network at home. So don't worry, you don't need to start figuring out how to type white blocks in. So at the very top there, we're going to build our wireless connection configuration, and we're also going to save that configuration to the board such that whenever the board receives power, if for whatever reason you didn't remind it about the wireless configuration, it would still be saved onto the board. And we're going to save that configuration to the board, and next time it powers on, it will connect out to our wireless network. We declare a couple of global variables. So what I'm saying there is LED, button 1, button 2, button 3 are going to be on pins number 2, 3, 4, and 5. We're then going to apply the pull-up feature on those button pins. It's just one of those little things you need to do, and make them inputs as well. So the board is going to be receiving data from those pins and not sending out data, just as we are at the very bottom there for the LED. We're then going to build some functions, and if you've seen Lua before, this is all Lua. One to turn on the LED, one to turn off the LED, and we're then going to enroll that into some additional functions which are actually going to do the talking out to Azure. There are definitely better and more efficient ways of coding this. This is just a good example for this presentation. So what we can see there is talk to Azure 1, it's going to make an HTTP post, it's going to connect out to that long complicated URL, it's going to submit the post in JSON, it's not actually going to submit any data whatsoever, and it's then going to output what the code result from the other end was. So if the code result is less than 0, we've got a problem, but if it's 202, which is the one that we expect to see, absolutely fantastic. And I repeat that 3 times for the 3 different buttons, and equally so, we then have the functions for the buttons themselves. Now, one of the things about the Lua language is it's designed around interrupts or callbacks or some method of saying, hey, I've been watching for these things to change. The moment they change, go and execute a function. So that's what we've got set here. GPIO.trig.trigger, button 1, whenever it sees that button do anything, so both go down or go up or change from 1 to 0, execute test button 1. At that point, it then figures out what button state it's in. Is the button pushed? Is it not pushed? Do I need to turn on or turn off the LED? Do I need to reach out to Windows Azure? So that's our code. We've got it in 99 lines there, including some very basic comments throughout it as well. So once we've gone and written that code, we then want to upload it onto our board and make it permanent. In this crazy piece of Russian software, we're going to load it up, tell it about the COM port that we're going to be talking to. We're going to hit the open communication button, and we're then going to reset the board. hit the factory reset button on that board. It will then connect out to that board, and at the very bottom there, you can see it saying Lua cannot open init.lua. And this is the very first file that board is going to try and open every time it powers up. So would you believe it? We've saved that basic button as init.lua. We're going to go to the upload button and we're going to send that to the board. It then says, hey, I'm going to upload this file, and then hopefully success at the end. Guess what you do at that point? Power cycle the board. Would you believe it? Once you've power cycled the board, once you've pushed the button, here we've got my shopping list at the top. I push the button, it reaches out to Microsoft Flow. Flow's got built-in reporting to it as well, so you can see that it's actually done something. You can see how long it took to do that, and the end result is I've now got milk in my shopping list. Hooray! Equally so, on that board, we've configured some serial output there, so kind of as a debug. So if we've got a problem with the board, we want to see what's going on, we've put some basic serial debug on there, and we've got turning on LED, I've turned on the LED, I'm turning off the LED, I've turned off the LED, and the success code 202 there for our post request. Now, one thing that I haven't covered in this presentation for this little bit so far is there's always niche cases like debounce on the board for those buttons. So debounce is the notion that when you push the button, if you don't quite push it all the way, it will hit the contacts, it will release the contacts, but you're still pushing on it, so it then makes the contact again. And that will ultimately result in it sending 2 requests. For this basic demonstration, I haven't factored that in, but there's no reason why you can't with a simple delay or some kind of a timer in that as well. So next on to plant monitoring. We've had the buttons, we've now got the plants. So I am in no means green-fingered. However, I do like to measure things like the moisture content of plants, so I know when to water them, so I don't kill them. So inside, we've got a little battery there. The idea of these batteries is that if you just leave them on and don't use the deep sleep functionality, this will survive about 17 hours. We then start turning on the deep sleep functionality. So inside these boards, they've got the ability to power down the radio, the ability to power down as many of its functions internally as is possible. And with a battery like this, you can achieve up to 6 months and sometimes beyond, depending on the temperature that the battery is inside. So in reality, you've got quite a powerful sensor there that you only need to change the battery once every 6 months. Now with these batteries, they're also rechargeable. And they're rechargeable through the USB port on the side there. And there's even a little LED to tell you when it's fully charged. Plenty of different options there around powering these boards, which is really quite nice, especially when compared to the Raspberry Pi, which is a challenge to power via battery on occasion. So the plan here is we're going to go to sleep mode, and then every 25 seconds, thereabouts. So the important thing is these boards, unless you solder one onto it, it doesn't have a real-time clock. However, it does have a notion of the measurement of time. And there's a command which you can execute to them, and it will tell you about how many microseconds it thinks it can sleep for reliably. And you can try and extend past that, and you'll probably get the board to crash, but you can give it a go all the same. So after that 25 seconds has elapsed, it's going to wake up. It's going to connect to the wireless network and test that it's connected. So it's important that we actually wait for that wireless connection to come up. It's then going to talk over this amazing thing called MQTT. It's going to send data to the Adafruit.io service, which is a free service with a paid-for option for the collection of IoT data. It's then going to allow 5 seconds for that message to be successfully sent and get back the response of success, and it's then going to go back to sleep. Now, equally so, those of you who want to spend more time on it, you can optimize this to absolute massive extent, whereby you make sure that you're waiting for that response instead of just putting an arbitrary 5 seconds in there. But we'll again, just looking at for basic demonstrations just for this presentation here. So MQTT is kind of the HTTP of the microcontroller world, where HTTP is going to be used on your web browser. So it works, or it should be the default choice for all IoT telemetry. It's really low power consumption. It has very minimal overheads, and it's designed with these little boards which are battery powered in mind. It can operate over HTTPS as a transport protocol as well, so there's security baked in. It's also working on the notion of a publish and subscribe model. So you publish data to a server as a client, or a gateway or a broker. And then equally so, you can subscribe to every time that information on that server changes. So this is a couple of images that I've stolen off the Adafruit website, which demonstrates how HTTP at the top left there works and how MQTT works. So HTTP is going to be along the analogy of we've got a toaster and we've got a cloud service, and the toaster is saying, hey, do you have any messages? And the cloud service says, no. And the toaster then says, what about now? And the cloud service says, nothing. And the toaster then says, hey, have you got anything? And the cloud service is finally like, no, go away. In the MQTT world, what we've done here is the toaster has subscribed to notifications from the cloud service. And that keeps that session open with that cloud service. So when the cloud service is like, hey, start toasting, that toaster can then start sending publish messages saying, hey, I'm at 50 degrees, I'm at 100 degrees, I'm 150 degrees. And then when that cloud service is ready, and only when it's ready, it will send another message back to say, hey, now it's time to stop toasting. Is everyone happy with the differences between HTTP and MQTT? Would you believe it that Facebook Messenger is powered by MQTT? You know, it's tiny little messages which, you know, we want to be as most and energy efficient as possible, and it's absolutely ideal for these kind of applications. So at the very bottom there, we've got some links to learn some more. So a quick sign up through the Adafruit.io service. No credit card required. It's a really nice, open, sensible service. Other ones are available. For example, Azure has their own one. Amazon has their own one. There are loads of ones that aren't just from the big companies as well. So once you've signed up, we're then going to start talking about sleep mode. So on these boards, to enable sleep mode, we're going to connect what is labeled on the boards as either D0 or GPIO 16, and we're going to plug that into the reset pin. And this is that little kind of action which executes to say, hey, to the reset pin, you need to wake up again. We can use the print node.deepsleep_maximum command to find out how long that board can actually stay asleep. And this is dependent on the temperature. And then equally so, when we want to go and send that board to sleep, we're going to go node.deepsleep and then give it a number value in microseconds, and then also what type of deep sleep we want to execute. So where 0 is the most power efficient but isn't absolutely ideal, no, other way around, where 0 is the least power efficient and 4 is the most power efficient, but it doesn't turn on the radio when it wakes up, which is a royal pain to work around. I'm just going to set it to 1, which is a value which works for me. So with our Adafruit.io service, we get on the kind of the free plan, we can send up to 30 data points a minute, which is no problem. At most, we're going to be sending 2 data points a minute. 30 days worth of storage at that rate, 10 feeds, so that's the different sessions, the different channels of data that you're going to be sending on it, and 5 dashboards. And dashboards is a kind of an overview of your data, so a way of presenting your data in a pretty view with charts and such like. So what we're going to do is go and create that first new feed. I'm going to call it soil sensor 1, and then I get the endpoint information. So if I was using the API through REST to talk to that, this is that endpoint string that I'm going to be plugging in. If I'm going to be using MQTT, which I am for this presentation, we've got the one at the very bottom there. With those settings in Adafruit.io, you can configure loads and loads and loads of other cool things, like privacy for your feed. So I've actually made this feed public. I stuck it on Facebook, and I'm sure no one's looked at it, because who wants to know the moisture content of some plant pots at my house? Equally so, you can share it with other Adafruit.io service users as well. You can configure notifications on that. So if your service goes offline for a long period of time, you get an email notification. Webhooks, there's loads of other cool things inside there. All that funky stuff that you can do. So how does this actually look? Now, when I was building this board, I accidentally destroyed the solder bridge which connects GPIO 16 to the reset pin. So I very quickly came up with a stand-in alternative which doesn't use battery power. Bit of a pain. Hopefully a new one of these boards has arrived in the post today. And you can see just about here, that soil sensor plugged into some very messy, dirty soil, but it does indeed work. So a quick zip through the code for this one. So again, we're going to configure our wireless network on there. We're going to save it to the board. And then we start configuring our MQTT client. So in this case, we've got a unique identifier for the board. We've got how long we want to keep that session open for. In reality, for this purpose, it doesn't need to be 120 seconds. We've got the username, which I'm using to connect to that service, and then the kind of connection key or the API key there hidden as well. Next up, we're going to configure that function, which is going to do that connect and send. So we've declared that we're going to connect to io.adafruit.com. We're going to do that over the secure port. We're going to do that with a QoS setting of 1. So there's a couple of different QoS settings you can apply. We're going to say when that's then collected. Equally so, we're going to read information from the analog to digital converter. So here we've got adc.read.0. We're going to read that information and then publish that to that feed which we've configured. Once we've done that, we're going to wait for 5 seconds. So there's a timer feature built into NodeMCU Lua there. We're going to say that we're going to sleep, and we're going to do that deep sleep for 25 seconds thereabouts. At the very bottom, we've got the bit which actually kicks everything off. So this is a timer which is checking that we're actually connected to the wireless network. So what we're looking for there is, do we actually have an IP address, and print that IP address to the serial once we're connected. So once we flash that to the board and once we've pressed go, we start getting pretty graphs and we can see what the soil sensor is saying about that. So at the very bottom here, you can see values, and that will be a value between 0 and 1,000. And you just have to gauge based upon how wet you think the soil is and how wet you think it should be, so you can start setting limits on this. As far as those dashboards go, this is an overview of the one which I configured. So I've got that line of how much moisture is inside the soil. We've got a matrix style feed at the top here, and we've got just a simple green light to say, hey, is the plant okay or not? Like I was saying, we can configure those triggers. So in this case, are we going to set a action when the soil sensor reads less than 500 and I now need to top up the plant? So today I've been talking about the ESP8266. The ESP8266 was the first iteration in a number of boards made by a company called Expressive, and it only has one analog to digital converter. Here's its successor, the ESP32. There are 6 analog sensors on there, so you can have a nice set of 6 plant sensors set up on one board. They are marginally more expensive, between 50p and £1. However, they are the newer iteration of the board. The code isn't as stable yet, but give it another couple of months, and I would say develop on the ESP32 by default. I've only got 5 minutes remaining, so I'm going to blast through this one like no one's business. 7 minutes. Oh, 7 minutes. Okay. So the final demonstration that I've got is my e-paper display. Until recently, e-paper displays of this kind of size were next to near impossible to obtain unless you're Amazon and making these things called Kindles. This screen was about £50 off Amazon. I think the price has gone up a little bit since then. It's made by a Chinese company called WaveShare, but it's a really funky, 7.5-inch e-ink or e-paper display. And equally so, they make their own board, which has the ribbon cable on it that you need to actually talk to this board without going through an additional driver board. So the plan here, and this is a work in progress still. So I haven't quite gotten around to formatting the output. Right now it puts everything on one line instead of splitting it up into multiple lines, and I haven't gone round to getting the wake up and go back to sleep bits going. To power this, we're using something called Azure Functions. This is effectively PowerShell or Bash or TypeScript or C# or F# or JavaScript run in the cloud. So Microsoft hosts this. Again, there's a free tier, there's a paid-for tier, and you can use all kinds of connectors to talk to this one. I know PowerShell, so that's what I'm going to use. And what we're doing here is we're reaching out to the Todoist API. We're plugging in my API key. We're formatting some dates. We're getting the project, which is for use with my home project, so things that I need to do around the house. We're going to plug that out into our response. So you can see that if we were to execute that as a REST method at the bottom here, it's going to output, submit gas and electric readings, go to https my.se, blah, 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 and also vacuum the house. I won't tell you which of those was overdue. To get the e-paper display working in Arduino, so at this point we've now swapped from NodeMCU to Arduino simply because there isn't support for this e-paper display in NodeMCU yet. There are for some of the smaller screens though. I just like the 7.5-inch one though because it fits nicely into a photo frame. For that we're going to download two libraries, the Adafruit GFX library, which includes pictures and other cool things, and the GX EPD 2 library. If you search for that on YouTube, you'll find a load of results on how to use that library. So blasting through the code, at the very top of our Arduino sketch, we've got loads of includes of libraries inside there. So the one which makes wireless work, the one which makes the paper display work, and one for a font as well. I mentioned some very basic thumbprint checks or some security certificate checks. This is one of those. This is the thumbprint for that Azure website that we're using that host for. Equally so, this is the bit which is going to connect out to the wireless network. It's a couple of delays inside there. It's going to say when we're connected. It's then going to start connecting out to our URL that we've configured. So here we can see it executing that GET request against the URL. We've got our host, the user agent inside there, and we're going to receive the information back from that as a string. The default response will come with a couple of slashes inside it and a couple of question marks and speech marks. So we're going to get rid of those. And then we've got gaps in my code where I need to learn some more things to actually make this demonstration complete. So for example, I want to read up a little bit more on how the fonts work, and I do need to split the code response into multiple lines. And you can then see at the very bottom here, we're actually writing information to the e-paper display. So what we've done is set the cursor. So we've got X and Y values there. We're then going to print a line to say jobs to do today. We're going to print a blank line, and then we're going to start printing the response that's come out of the web service. And that's exactly what's displayed on here. That's the response from the web service. Feel free to come up at the end of the presentation and have a look. Happy with that? Wow, it's a lot of information. So final two slides. I used to work for Oxford. I don't work for Oxford anymore. I now work for this company called AN Security, and they've asked that I put two slides in the end here to talk about something which is kind of actually relevant to this presentation. And this wasn't the driver for that presentation. So for those of you who are in colleges and are interested in the notion of per user VLAN, so every student has their own VLAN. There's a company which has just come into the United Kingdom that we're now working for, or working with, called RGNets, and they can do that. Right, so if you're interested in this kind of awesomeness, get in touch with me at the end of the presentation and we can set you up with it. I don't have that much time to go through questions, but final slide on that, it will do dynamic pre-shared key-based technology. So if you've got students who have got printers or their Amazon Alexa and they want to plug that in their student dorm, fantastic, we can do that. We can stick them all in their own private VLAN as well. Speak to me at the end of the presentation. Okay, questions time. Now, if any of you have ever been to one of my presentations, for asking questions, there are usually prizes. Those prizes are ESP8266 microcontrollers. I only have 4 of them. Does anyone have any questions? Go on then.
What sort of range have they got? Like Wi-Fi?
I've not done any serious testing. The antenna on them is tiny. The power output, 250 milliwatts, is what they're kind of operating in. Tiny. I don't know, maybe 25, 50 meters at best in ideal conditions. Certainly inside my flat inside Oxford, and those of you who know Oxford, the flats are pretty small, I've never had a problem with it.
It goes through about 4 or 5 walls.
They're so very light. Okay, go on, you.
Your e-experience, is it also touchscreen?
No, it's not. So the ones I've been thinking there is put a row of buttons along the side, maybe, and I can tick off the jobs like that. I haven't seen one which is touchscreen yet. I can only imagine it's a matter of cost. Go on then.
How much power does it take to run the screen? And have you tested the battery life? How long does it stay up?
I haven't. So the thing with the e-paper displays, of course, is they're power consumption when they're changing is going to spike, but once they've changed, no power required. You stick that in deep sleep mode.
So it depends how often you change your
Yeah.
material.
And the time it actually takes to change that display is between kind of 1 and 6 seconds. So it's not as fast as your Amazon Kindle, but you know, it's still good enough for information which doesn't change on a regular basis. You know, the bus stops would love this kind of technology. I need to choose someone else from Cambridge. So go on then, you.
Yeah, good question. Can you connect it to something that will water the pipe when it's running out?
Exactly, why not? So you've got spare digital pins there. Connect one of those digital pins to a little pump. The little pump chews up some water from a glass you've got next to the plant, feeds it into the plant. What, of course, you then need to do is have another sensor inside the water there to tell you what the water level is. And at that point, you need an ESP32 so you can get extra analog readings.
Have you played with the seed alternative?
No, I've not. Go on then. Talk to me.
Seed do same chip as that, but tailored with an Arduino, so an app mega, and then hardwire the serial port between the two chips together.
And you get chip-to-chip communication.
Chip-to-chip. That means if you're doing bit banging stuff, you get the power of an Arduino. And you get the Wi-Fi of the... Yeah.
So, I mean, the grand scheme here, I've been working with these chips for maybe 6 months. My actual time with, you know, proper development time is probably only 20 hours or less, maybe. I'm just scratching the surface. And this is what you can do by scratching the surface. Spend some more time and just imagine what you can do. So, final takeaways from me. This video, assuming OBS recorded it correctly, I'll publish it on YouTube. Head to myworldofit.net and you'll see this video and maybe even the slides. I'll see if I can get them to the CITC guys to publish via email as well. If you want to get in touch via email about this presentation, there's my personal email address. And if you want to get in touch about work stuff, there's my work email address. Some final takeaways about where to go out and find some more. There are 3 really good YouTube channels which I would recommend to find more about microcontrollers. Andreas Spice, he's Swiss-German talking but speaks English. Absolute legend as far as I can tell. He does stuff with this technology called LoRaWAN. And this is taking Wi-Fi and then extending it to 70 kilometers with a tiny little antenna. Obviously, the data rate goes down massively, right? But, you know, if you're just sending what the plant is doing and it's 70 kilometers away, crack on, you know, right? Adafruit Industries, they've got some brilliant videos of just their products and all the cool things they do. And, of course, Hackster.io as well. Last chance for questions. I don't have any more prizes. Chris?
Is it something when you sort of change your code, is there sort of a risk that you can brick the device, or is it sort of fairly safe?
So there's 2 elements to the board itself. One is the bootloader, which you can't really change or break or brick without ripping the chip off the board. And the other is the firmware. The firmware you can flash, and you can flash it until you eventually erasably kind of break the flash memory that's on side there. I haven't done that, and I've flashed some of these boards a couple of 100 times now. So I should imagine not. Anyone else?
How much are the sensors?
So the plant moisture sensors for a pack of 2, they were about £10 for the high quality ones. The ones which I managed to kind of do a little bit of electrolysis with accidentally, they were about £2 a sensor. You can buy kind of starter kits, which are really, you know, designed for teenagers and people just starting out in electronics, which includes a range of sensors, includes an Arduino Uno R3, or includes an ESP8266 for about £30. And you get a light sensor, a piezoelectric sensor, you know, a real-time clock, all of those kind of things in a kit for £30. It's a really good place to start, and that's what I did.
Just the same technology that Amazon uses for the resale.
Oh yeah, so the little Amazon tokens. So what I've effectively made here is one of those buttons at a much lower cost that if when it runs out of battery power, I don't need to buy a new one. I should imagine so. So there's particularly for the NodeMCU Lua ones, where you can actually set it up in a very similar fashion, whereby it hosts its own SSID. You connect to that SSID, you then give it the username and password for your pre-shared key network. It embeds that, and as long as it can talk to that network, it won't broadcast its own SSID again. So, you know, there's some very powerful things that are just baked straight in there, like that kind of functionality, like the ones that you can get out of the Amazon buttons. Really running out of time now, so any last questions?
Would that
LoRaWAN, could you make some sort of messaging service between
Yes.
people?
I have, right. So my girlfriend is currently deployed all the way down at Comanche's Naval Base, Devonport. And I thought, right, if I got a balloon and hosted it, you know, kind of a couple of miles up into the sky, I could probably get the range. You know, there's no reason why you wouldn't be able to do some kind of messaging service. It's, you know, it's ideal for that kind of thing in an IoT context. So, yeah. Anyone else? Cool. So the CITC guys have told me that regardless of what it says on your timetables, the next step is to go to the planetarium. So thank you very much. If you want to see the boards, here's the boards. Otherwise, go to the planetarium.